G'day guys, a lot of people have been asking me about how index laws or indices are going to be used in their exams or what sort of questions they can look out for. So what I've done is I've just gone to a past exam and just pulled out what I think is a sort of a standard index law style question where it's just asking you to use index laws to solve or simplify some of these expressions. So what we've got is we've got a mixture of different index laws or different techniques in these four different questions. This whole total question gives us a good cross section of different techniques that we need to be able to master to go well in exams when we're asked about index laws anyway. So without further ado, let's get to it. So we'll start up here. So this is question A, number 1. So express as a power of a to the x times a to the y divided by a to the x minus y. Alright, so just for your benefit guys, we're going to use two index laws here. The basic ones, we're going to have a to the n times a to the m is equal to a to the n plus m. And we're going to use the corollary of this, a to the n divided by a to the m is going to be equal to a to the n take m. Cool. So with these two index laws in mind, we're going to solve this first problem. So a to the x times a to the y is going to be a to the power of x plus y. And then we're just going, in our first bit of working out, we'll just divide that then by a to the x take y. Cool. So what we can do now is, because we have this divide by, we're going to use this second index law here. So I'm going to go, well, this is equal to a to the x plus y subtract, now I'm going to put this in a bracket because you'll see why in a sec, x minus y. Cool. So we then compute this. We're going to have a to the power of x minus x is just going to be a to the power of 0 with regards to the x. And we've got a to the power of y minus y, so plus y. So we have a to the y plus y is 2y. And that is our solution for part A number 1. Part A number 2. Let's just separate them. So we have A part 2. So 16 over 9 to the power of 3 over 2. Now, what you can hopefully see is that 16 and 9 are both square numbers. So what we're going to also use is we're going to use the distributive index law, or we're going to use, or you could call it, we've got a to the power of n all to the power of m is a to the n times m. And with regards to this one, we're going to use this index law as well. A over b all to the n is equal to a to the n over b to the n. So that's the distributive law there. When you have in brackets, we have a divider of times inside the bracket, we distribute the power over all of the terms inside the bracket. Okay. So how is that going to help us with this one? Well, first of all, what I'm going to do is I'm going to express the 16 and the 9 as as powers of 2. So I'm going to write, well, this is equal to 4 to the power of 2 over 3 to the power of 2. And that's going to be to the power of 3 over 2. Now, the reason I do that is because when I multiply the power into the bracket, I'm going to have 4 to the power of 2 times 3 over 2 over 3 to the power of 2 times 3 over 2. And this is like 1.5. 2 times 1.5 is 3. So this is going to equal 4 to the power of 3 over 3 to the power of 3. Now it's going to ask you, you won't be able to leave it as numbers to a power, so we're going to have to compute 4 to the power of 3. Well, that's 64. And 3 to the power of 3 is 27. Just a word to the wise guys, in exams, it's going to be good if you have like all of these like low numbers, like up to 5, maybe even 6 to the powers of 1, 2, 3, and sometimes 4, just off the top of your head. So you can just know what 4 to the power of 3 is. 5 to the power of 3 is 125. All of these kind of things. It'll make your life in exams, especially when we've got, this is in a non-calculator section of an exam, so we wouldn't be able to use our calculators in this part of the test. So it's important that we can do these quite quickly. Okay, so let's just separate this again. Cool. Now, we're on B number 1. Okay, so what have we got? The square root of 3 to the power of 2x plus 4 equals 27 to the power of x. Okay, so what we're going to use here is, the method we're going to use is we're going to try and make sure that the bases are the same on both sides of the equality. So the left-hand side here gives us an understanding or a hint about what base we're going to use, which is 3. So we're going to make sure 27 is expressed as 3 to the power of something. So, and I'm also going to rewrite, so the index law, the new index law we're using here, is the nth root of a is equal to a to the power of 1 over n. So, in this case, I'm going to have, I'll put it in a bracket, 3 to the power of 2x plus 4 to the power of 1 over 2. So that's the square root rewritten as a index is equal to. Now I'm going to express 27 as 3 to the power of 3. I'm also going to put that in a bracket. Cool. Now we have the same bases on both sides. I'm going to multiply out our brackets. So I'm going to multiply 2x plus 4 by a half. So this is going to be 3 to the power of x plus 2 is equal to x times 3 is 3x. Now, the reason we want to get both of our bases the same is because from here, if the bases are the same, we can equate the powers. So we can say then, therefore, x plus 2 must equal 3x. We take the x to the other side. We've got 2 equals 2x, or x equals 1. Cool. So, again, we're going to use that exact same sort of strategy to solve this next one, B part 2. Solve the following simultaneous equation for A and B. Okay. What I'm going to do is I'm going to make sure that the bases on both sides of the equality are the same. So I'm going to rewrite this simultaneous equation as 2 to the power of A plus B equals 2 squared, and 3 to the power of 5a minus 2b is equal to 3 cubed. So that's 27, and that's 4. Now what I can do from here is, like this problem, I can just remove the bases. If the bases are the same on both sides of the equality, we can just equate the powers. So I can have, for this problem, a plus b equals 2, and I can have 5a minus 2b is equal to 3. So, again, because I'm going to use the substitution method, so I'm going to say in this one, b is equal to 2 minus a. And that I'll put an underline under that because that's going to be useful for me later. I'm then going to substitute b into this second function. And I'm going to have 5a minus 2 minus a equals 3. So this is going to be 5a minus 4 plus a plus 2a, because minus 2 minus a is plus 2a. So 5a plus 2a, sorry, is 7a. Minus 4 equals 3. Then I'm going to have to try and write nice and small here. Take the 4 across, we're going to have 7a equals 7, and then divide by 7, a equals 1. Cool. Then I can substitute 1 into b. b equals 2 minus 1. Great. Okay, so let's go through these problems just quickly. The first problem, it was just a matter of remembering the first two index laws we ever learned. That if we multiply two numbers with the same base, we can add the indices, and if we divide two numbers with the same base, we can subtract the indices. The only tricky part here was making sure that we stuck the x minus y from the second one in a bracket. So we minus x, but then we plus y, because if you take a negative y, it's going to be plus y. So that's the only tricky part with this one, I would say. So let's just put a little asterisk there. That's the only bit to make sure of here. The second one, we're using the fact that if we have a bracket, we multiply the indexes and we apply the distributive law, which can also be written like this. If we have AB all to the n, this is going to be equal to a to the n, b to the n. So it works for division as well as multiplication. So what we did here is we recognized that 16 and 9 are both square numbers, and we expressed these as numbers as like 4 squared and 3 squared. What we then did is we used the fact that they were squared for when we multiplied the 3 over 2 in, the 2's cancelled. That's what happened here. So then we were left with 4 to the power of 3 over 3 to the power of 3. Now this we then said was equal to 64 over 27, and I made the note at the time that in an exam situation where time is critical, it's probably good that you have a lot of these small powers under control, like straight away, like your times tables. Cool. So I would say that that's probably the main bit there. Now, what we did here is we introduced a new index law which involves surds, and we use that to express the surd as a fractional power. After that, we then multiplied. And what we also did as well is we made sure both sides of the equality were the same base. The reason we did that is because when we've multiplied out the brackets, if the bases are the same on either side, we can forget them and just equate the indexes. So that's what we did, and then we used some pretty basic algebra to solve it. So the important part here for this question is to make sure the bases are the same. Finally, this one here, we exploited the same sort of strategy as we did with the one before it, where we made sure that the bases were the same on both sides of the equality, and then we equated the powers. Then I used the substitution method for simultaneous equations to then substitute b into one of the other equations to find a and then b. So Yes, there's a few different things we had to do here. There are a few different tricks of the trade. But if you do enough of these, finding out or looking at what you have to do will become intuitive. You won't actually have to think, oh, I've got to make sure I use this index law. It'll just work after a while. But again, with these sort of questions, like I think this question may have been worth 8 marks overall. So, it's quite a lot of marks. If you can get these down, you can do these questions quite quickly. So it's a good part of the exam to sort of make sure you can lock these bits away. So I hope this video helped, guys. If it did, give it a thumbs up. Do my channel a favor and subscribe. I need all the subscribers I can get. But until next time, enjoy your maths.